very much, I know very well that sun and swimming pool has much more attraction power than talk about security, and so I beg your pardon. So, anyway, so my name is Gianluca Dini. I am from the University of Pisa. Just a few information items about my university. The university is, of course, the University of Pisa is in the central part of Italy, on the west side, on the west coast. I think that every one of you has heard at least once about the Leaning Tower, so my university is very close to the Leaning Tower. The university was founded in the 14th century, so it is quite old, and we had glories, Nobel Prizes, and Fields medalists. Nowadays, the university is organized in 20 departments after the 2010 reform, and we have around 50,000 students, which make us a medium-sized university for Italian standards. And the number of people doing research and teaching is around 1,500. So because my university covers all the disciplines, from engineering to math, literature, philosophy, and so on. Okay, so my research interests are in the field of security, mostly in the field of security, especially in these last few years. And I do research in classical fields of security, for instance, the network security, operating system security, but I have been involved in a number of projects. Part of them are European projects, national projects, other kind of projects financed by industries, dealing about security in embedded systems, in particular in wireless sensor network scenarios, robotic systems, underwater acoustic networks, and so, in scenarios that are not the classical network or operating system environment. And I have faced with typical problems in security within these application scenarios. So, in this talk, I am going to talk about the activity and the results that we have achieved in the Planet project. This morning you had an overview of the project, so I'm not going to spend any more words about this. I just remember you that the project aims at defining a platform for planning, deploying and maintaining systems composed of sensors, actuators, and autonomous vehicles, both terrestrial and aerial. Okay? And of course, in this kind of systems, security is a problem, because if I have any security infringement, then I might have two vehicles which collide into one another. Okay? So the nice thing of this project is that security has been considered as a first-class problem. This means that security has been considered as a requirement, as a basic requirement, since the early stages of the project. So it is not a patch, it is not an add-on, something which comes later, but it is something that has been taken into consideration since the first day. The other thing is that, I will come back on this point later, but the other thing is that we move from concrete scenarios, and we make realistic assumptions. So we don't try to modify reality in order to comply with our theories, but the other way around. So a very engineeristic approach. And also, although we are a very small group, and we are the only partners dealing with security in the project, we try to have a comprehensive view, not only focusing on a small piece, for instance, on a key management scheme or on encryption algorithm, but we try to have to face security and to consider it, let's say, in a very broad way. So from the designing phase, in the architecture definition, and also finding some specific solution to specific problems. So we brought several contributions in the project. We achieved several results. I think I listed here the more important. In particular, for the design phase, we investigated the impact of security on performance. Always keep in mind that security wants CPU cycles and wants bandwidth. Therefore, any security solution competes against the application for resources. So every time you have to establish a trade-off between security and performance. And in particular, we investigated the impact that the security sublayer of 15.4, I assume that every one of you knows the standard, because I think every one of you is playing with wireless sensor node for a while, so you must know this communication standard. It has a security sublayer, and so we investigated the impact that security has on the performance of the wireless sensor network. In addition, we also defined a framework and a set of tools to investigate the effect of an attack on the system. And I will talk about this more in depth in the following, because I think this is a very useful tool in the designing phase. We designed a security architecture. In particular, we focused on the security architecture on the node with two aims in mind: transparency and reconfigurability. And I also spent a few words about this. And finally, we solved specific problems. We, let's say, defined specific schemes, security schemes, key management schemes. Like and HIS are two key management schemes that we have proposed. I'm not going to talk about that, but if time allows me, I will talk you about this countermeasure against selective jamming, which is a particularly insidious form of denial of service that may come up in cooperating object system, a wireless sensor network, and even in IoT system. All the activity that all the results that we have achieved are reported in papers that you can find on my own page, and I would be very glad if you want to discuss with me about them, you send me some feedback and so on. I would be very glad. So let's start with the first let's say, issue. So the evaluation of the attack, of the impact of an attack. Okay, this is an important thing, especially in the design phase. Okay. So let us consider a wireless sensor network, but these considerations apply also for IoT systems. So I am not going to say why these technologies are important, why they achieve a certain level of success, at least in the academic world. Anyway, in this kind of systems, we have security problems. Okay? It is a fact that in this kind of system, a security infringement may easily translate into a safety infringement or in a privacy infringement. Okay? I have a cooperating system. I have, let's say, autonomous vehicles who have to coordinate. For instance, they have to share the same space. They have to avoid collisions. If I have an adversary who is able to, let's say, compromise the collision avoidance protocol, then it is easy that the two vehicles collide into one another. And when two vehicles collide into one another, there is no way to roll back this transaction. Okay? So a security problem can easily become a safety problem. Okay? So this is very important. And that is why we consider security as a first-class problem. It was a requirement that we consider since the beginning. Security is in a wireless sensor network in IoTs is a bit different with respect to security, let's say, in network computing, desktop computing, or server computing, so normal network environment. Okay, first of all, because communication is wireless, and for an adversary kept by means of a radio transmitter, is very simple to eavesdrop messages or inject packets. Okay, but also because sensors and things are deployed in environments which may be unattended or which may be even hostile. Okay, and since they have limited resources, for cost reason, okay, limited resources in terms of computational resources. On a sensor node, it is very difficult to run public key encryption. Okay, if you run RSA, it takes minutes. Okay, or you don't have any hardware mechanism similar to the mechanism that you have in your laptop, or you don't even have any physical protection means that you can find even in the cheapest smart card. Okay? So these two things make it possible a situation in which your adversary puts its hands on the sensor or on the device or on the thing and is able to physically attack, to reprogram, to compromise the node. Okay? So the castle model, where you are the good guys inside the castle and you have your walls and the adversary is outside, does not work anymore in this kind of applications. Maybe the Macbeth model is more adequate, where your adversary is within, maybe within the system, just because he is able to compromise your devices. Okay? Well, notwithstanding this, let's say research about the wireless sensor network is quite mature. So it is not anymore in its infancy. Okay, it is quite mature. If you, for instance, query the IEEE or the ACM digital libraries by using this string as a search key, then you retrieve thousands of results dating back to the beginning of 2000. So there is a lot of literature for this, and we may say that attacks and related countermeasures have been investigated under any possible assumption and constraint. Okay, so basically we can roughly say that for any problem that comes in our mind, we may find a solution in the literature. Okay? So this means that we can sleep easily. And this is not actually true. And the problem comes from reality. Let us suppose that you are going to design a system, an IoT system, a wireless sensor network system, and then you start thinking the attacks that can be played against your system. Then I am sure that you can put down a list of tens of attacks. The point is that you cannot defend from all of them. You cannot do that because of usability reason. If you do that, your system becomes completely unusable. For performance reason, as I said, security competes against application for resources. So if you try to defend against every possible attack, your performance completely falls down and the cost raises up. Okay? So you cannot defend from any possible attack. So the question is, which are the more relevant attacks that I should consider, which I should defend from? Okay? And the point is, what does relevant mean? An attack may be relevant because it's very feasible, it is very simple to do, and even a newbie can do it, or because it may have a strong impact. Okay, so the relevance of an attack can be measured along these two dimensions. Okay, and this is what you do when you actually run a risk assessment phase. And please remember the talk by George yesterday, who mentioned the risk assessment in the case of privacy, and we are talking about risk assessment in the case of security, but more or less methodologies and ideas are the same. Okay, so when you are designing your system, then you have to make this choice. You have to answer this question, and you have better find an answer just before deployment, because afterwards it may be too late. Okay. So within the project, we try to answer a part of this question. In particular, we try to evaluate the impact of an attack. So given an attack, what is its impact? Of course, we would like to do this in a quantitative way. If I say, okay, my adversary is able to inject packets in my network, every one of us is able to, in a qualitative way, to state that, okay, that those messages will create some problems. To which extent? Can I measure the problem, the effect of these messages? Okay, because this is important. If for each attack I am able to measure its impact, to assign a number which says how strong the its impact is, then I am able to rank the attacks and to say, okay, this attack is more important than this attack. I will focus on this, I will neglect this. Okay, this is more or less the idea. Okay? A tool to do this. We cannot do this activity, let's say, in a qualitative way, we need a way to extract those numbers. So we have, in order to do that, we have designed and implemented a framework which is based on simulation. There are other approaches. For instance, other colleagues prefer an analytical approach. Okay? This is particularly, in particular, colleagues working in security in industrial systems, they prefer an analytical approach, even though mostly because in industrial system it is simpler to abstract away the system. You can abstract away the application, you can abstract away the control, you can use transfer functions, and so on. So you can address the problem in a mathematical way. In a system like a wireless sensor network or an Internet of Things, it is very difficult to abstract away the system in a set of formulas. Okay? And even though you are able to do this, you are going to miss all the details, for instance, related to the network. Okay? So that's why we prefer to follow the simulation way rather than the analytical way. Of course, you can always choose the experimental way in order to evaluate the effect of an attack, but not always you can experiment on a real system what's the effect of an attack. And there are many examples that comes into mind, and I don't need to tell. Okay? So, basically, in this framework, a designer can do the following 3 steps. Describe attacks, reproduce their effects, and evaluate their impact. I would like to stress the fact that a designer, so the framework reproduces an effect. So we are not interested in reproducing the attack. So we are not doing penetration tests or similar. We assume that the attack are always successfully performed, and then we would like to see what are its effects. So we are not interested in reproducing the attack. This has to do with feasibility, which is important, but it is another part of story that I am not addressing here. Okay? So this means that if my adversary is able to inject messages, I'm not interested in describing how he actually injects messages, which technology he used. I don't care in this phase. I just want to reproduce the effects. In other words, that some fake message at some point starts to pop up. And I want to see what the effect on the system of this message. Okay? Of course, in order to evaluate the impact, I need to define metrics. So in the next slides, I will just give you a very, very quick overview of the framework and on the metrics that we have defined, and also I will present a very simple example, just to give an idea of what you can do by means of this framework. The framework basically is composed, so the main components of this framework is an attack specification language. It is very simple language. I'm not going to enter into details, but it is a very simple language that allows you to define both physical and cyber attacks. In a very simplistic way, a cyber attack is an attack that you perform against a message. You eavesdrop a message, you change a message, you delete a message. Whereas a cyber attack is an attack that you perform against a node. You smash a node, or you move a node, or you reprogram a node. Remember that in our threat model, the adversary is can be inside the system. So the adversary can physically act on the nodes. For instance, can smash to break a node, to smash a node, or just simply move a node away. Okay? The language also allows you to, let's say, define complex attacks, where a complex attack may be composed of several physical and cyber attacks. Okay? So you can define quite complex attacks. Why this does not? Okay. This is just a very simple example. The wormhole attack, I guess that every one of you knows what a wormhole attack is, or not. I see many blank faces. Is there anyone alive there? Okay, so a wormhole attack is a very powerful attack. So this is the network. Okay, you have nodes, sensor nodes. Okay. And then, for instance, let us suppose that your adversary is able to install a computer, another computer here, and connect the two computers by means of high-speed link. Okay? So when this node, let's say node A, broadcasts a message, and let us suppose that this is its broadcast domain. This message is received by the adversary, which tunnels the message in a remote part of the network. And the message is then broadcast again. So, if you apply this attack to any routing attack, and if you assume that this is an hello message, this node B believes to be a neighbor of A, whereas in reality it is not. Okay? And by means of this attack, you can destroy any routing algorithm that I know of. Okay? So this is just to give an idea. So in order to describe this attack in our system, in order to evaluate the effect that such an attack can have on a wireless sensor network, then by using the language, you can do it just in a few lines. This few lines says that for every message sent by node 3, this message, so this is node 3, this message is tunneled, is forwarded to this list of messages, to these nodes. Okay? So by means of these few lines of code, you can describe this attack. I repeat again, I'm not here by means of those lines of code. I am not describing how the way the adversary implements the attack, but I just describe the effect of the attack. And the effect is that a message which is that is sent here will at some point pops up in a part of the network where it is not supposed to be. Okay? So once you have defined the attack you want to evaluate, then you have something similar to a compiler, which compiles the attack in a language that is understandable by a network simulator. Okay? Once again, we haven't built a new simulator. We wanted to use off-the-shelf simulators. Okay? In particular, we have used Omnet++. We have used Castalia, which is a wireless sensor network based on Omnet++. So we didn't invent a new simulator, but we used an off-the-shelf simulator, and we extend the simulator in order to manage the events that are related to the attack. Okay? We did a very pragmatic approach. And all these events are managed in a transparent way with respect to the simulator itself, so that if you want to evaluate another attack, you don't need to change the simulator, you don't need to change the network simulator or the application simulator, but just it is sufficient to describe the new attack, recompile it, and execute it. Okay? The architecture is quite general, so we have specialized and implemented this architecture for wireless sensor networks. This is just for a matter of resources. We are a small group, but there is no problem in making another implementation for instance, Wi-Fi or for other network technologies. Okay. Of course, there is no magic here. Okay, this is not a country for newbie. If you want to describe an attack, you must know all the details. You must know how the application works. You must know the network topology, protocols, and so forth. You must know as much information as your adversary knows. Okay, here the network simulator is not able to read in your minds. You have to describe the attack, and you have to know all these details. But whenever you are able to describe these details, then you can, whenever you are able to master these details, then you can describe an attack and then simulate it. Just a few intuitions about the implementation. So this is the original simulator. Okay, this is the original Castalia simulator, which simulates sensor node. Okay, in particular, this module simulates the network 15.4, and this component, this module, simulates the application and the sensing. Okay, we just added this module. That's why I used the word, we extended the simulator. We just added this module, which transparently to these two modules intercepts events, manipulates events, injects events in order to simulate the effect of an attack. Okay? So in an injection attack, this module just injects messages in the appropriate receiving queues of the appropriate modules. Okay? But everything is done in a transparent way with respect to these two modules, which are unmodified. Okay? Of course, if you want to make more complex attack, if you want to describe more complex attacks such as the wormhole attack, then you need that nodes cooperate, because this could be the part of the simulator which describes this node, and this could be the part of the simulator which describes, for instance, this node. So this means that the two local modules have to be coordinated, and we use a third kind of module, which is the global filter, which makes it possible to coordinate, let's say, the nodes in order to implement more complex attack. Also, this coordination is completely transparent with respect to the original network simulator, which is, I repeat, unmodified. Okay? So, now we are able to, let's say, describe an attack. We are able to simulate an attack. So now I am going to spend a few words in discussing an example to hopefully convince you that this tool is useful. Okay? So, in cooperation with our colleagues from chemical engineering, we investigated this case. Let us suppose that you have a chemical plant or industrial plant which has 3 smokestacks, okay, which emit pollution. Okay? And according to rules, to laws, pollution must be below a certain threshold. So the idea is to deploy a wireless sensor network to monitor the pollution production of the plant and to check whether each smokestack violates the rules that are established by law. Okay? The network is clustered, so I have a cluster for each smokestack. The cluster is composed of a number of nodes and a cluster head. Periodically, the nodes transmits their measurements to the cluster head. The cluster head makes some computations so that you can think about average, just to fix ideas. And periodically, the cluster head transmits their report to the sink. Very classical architecture. Okay? Let us suppose that in a normal case, in a attack-free condition, I have one smokestack, let's say smokestack number 1, which for some reason produces more pollution than it is allowed to. Okay? So in cases like this, an adversary may try to attack the system in order to make the smokestack 1 behavior appear as normal. Okay, so the smokestack is polluting, whereas the adversary attacks the system and in order to lead you to believe that the system is working correctly. Okay? And an adversary has several ways to do that. So let us suppose that you are a consultant of this company and you have run your threat model and you have realized that the 3 possible attacks that your adversary can play are an injection attack, simply putting message in the network, a misplaced attack, so the adversary takes a sensor and moves it away from the smokestack. This sensor is going to measure a reduced amount of pollution, simply because it is farther than it is supposed to be. But this measurement is linked to its supposedly original position. So the computer is completely broken. Okay? Do you get the point? The other attack, which is even more subtle, is that I take the sensor, I move it away, but in a particular place. I move the sensor from smokestack 1 and I put it in the cluster of smokestack 2, which works correctly. So the sensor makes correct, let's say, measures a correct amount of pollution, and then by means of a wormhole forwards this reading to its own cluster head. Okay? So the first attack is purely cyber, because I just put messages in the network. The second one is purely physical, because I take a sensor and I move it away. The third one is cyber physical, because I have a physical part, I move the sensor, and I also have a cyber part, which is the tunnel. Okay? So 3 different attacks. The point is, which attack is more relevant? So which attack I should consider with more attention? Which attack could create more, let's say, damage? Okay? And it is very difficult to say without, let's say, intuitively. You can have the intuition that each attack can create problems, but it is difficult to say which one is more effective than the other. Okay? So here I put a number of parameters for the simulation, and I'm not going to explain all those figures or those parameters, because otherwise it would take years. The injection attack. Intuitively, you can assume that so the injection attack is very simple. An adversary pretends to be node number 4, and then puts messages in the network where the value is just 33, which is below the threshold. So just put fake messages in the network, pretending to be another node. Of course, the transmission rate can change, and by means of the simulator, we evaluated 4 different transmission rates. Okay? And by means of the simulator, we realized that in order for the attack to be effective, the transmission period must be less than 50 milliseconds. But it is sufficient. There is no reason for being less than 35 milliseconds. Okay? This is just the first result. Okay? And here you have the curves related to the different transmission periods. We made the simulation for the second attack. In this case, the attack, let's say, variable was the distance I move the sensor. Is it sufficient that the adversary moves the sensor 2 meters, 5 meters, 10 meters? Okay? So by means of the simulation, we realized that the displacement distance must be at least 5 meters. If the sensor is displaced less, the attack is not effective. You must displace the attacks 5 or more meters, please.
So you try to affect the level of pollution? I mean, I'm wondering, in the first attack, how do you manage? I mean, what's the problem when I try to inject like a lot of parts into the system? The problem is that they are like with a fake value, right?
Yes. And okay, once again, we have at least some other indication about so we are refining the attacks. And the first definition was quite high level. Now we are refining the attacks, and we are, let's say, finding constraints under which the attack may be effective or not. Similar story for wormhole attack. I'll make it very short. And we realized that it is sufficient to move node 5 into cluster 2, and then the, let's say, transmission period, it must be around 35. Okay? Okay, so now basically we have defined 3 attacks, and we have simulated each one of them. And we also got some more information about their effectiveness, about the constraints under which they can be played. The problem, however, our initial problem has not been solved yet. So which one of them is more important than the others? Okay? In order to do this, we have defined metrics. We define metrics. We define a metrics for integrity, The three attacks I have presented are three attacks against the integrity of the system. Okay? Because I am trying to alterate the correct functioning of the system. But of course you can define a matrix against availability of the system. I may try to stop the system working for a while, okay? Or again, confidentiality. This is not our case, but there are attacks which try just simple to steal information, and information is the value, and then by means of this value you can, let's say, measure the effect, the effect of that attack. Okay, so you can define a metric for each kind of attack. And if you have a very general attack, you can mix the three metrics together. So I'm not going into more details. You can find the details in the paper. I just have to, let's say, spend credits for Cardenas, Rusta, and Sastry because we extended, regarding the metrics, we started from their work and we extended it and refined their work. For people who works in the control field, Sastry is a very well-known author. So we started from their theory, and then we moved on. But of course, I have these credits. Anyway, so as to the service integrity, the idea is very simple. Okay. Let us suppose that I have a node which receives S messages. But the messages does not contain the original value, but they contain a fake value. So basically, I compute the average square error. So this is the original value that I would like to receive. This is the fake value that I actually receive. And I evaluate the average square error. And this average square error is then averaged again over the number of messages, over the number of nodes which receive fake packets. Okay? But I mean, all the mathematical details are in the paper. I don't want to spend time into explaining these form equations very detailedly. The important thing is that by means of this formula, I am able to produce a number, which represents the impact of the attack. Because, for instance, okay, so this is before the attack starts. Okay, this is V, for instance, and this is V prime. Okay, because this is what I would receive if the attack is not present. This is what I receive in the presence of attack. So this is V and this is V prime. So I have all the data. So the simulator has all the data to compute these formulas. And when I compute these formulas, I produce a number. Then I can attach to every single attack. And then I can, let's say, define this list. A wormhole attack where the adversary transmits 23 packets per second, its impact is 57. A misplaced attack where a node is moved away by 2 meters and its impact is around 1. So this attack is much more effective than this one in a quantitative way. So these attacks, the wormhole attacks, are more relevant, for instance, than a misplaced attack. Okay? So in this way, I can quantitatively evaluate an attack. I attach the number, and I define a rank in terms of impact. Which attacks have more impact than others? And this is what I wanted to do, the problem that I wanted to solve at the beginning. Questions?
So there we have the details of the attack. But how can we compare a wormhole attack with a misplaced attack if they have different numbers.
In this way.
I mean,
Simply this way. So you have a way to compare that.
But maybe with 50 packets per second, or with 15 meters, this place would be
Yes.
worse.
Right. Yeah, yes, right. So the point is, how can I figure out these values? So they are not, let's say, selected at random. In order to figure out these values, well, this requires some, let's say, some expertise. So you have to have played risk assessment for a while for a number of cases. You have to talk, for instance, to the manager of the plants and to understand, for instance, if you have an intrusion detection, then the intrusion detection may detect if the traffic goes beyond a certain threshold and so on. Or, for instance, how do you select these meters? This may also depend on the physical, the logistic issues of the plant. So 2 meters, 10 meters, maybe small, maybe large. It depends if there are fences. It depends if there are guards, which from time to time walk around and so on. Okay? So this is perhaps the most difficult part because strongly relies on the physical, realistic assumptions that you have to make on the system. And very often you cannot make these assumptions yourself. You need the collaboration of the experts. In this case are the chemical engineers and those who are entitled to run the system. Okay? Okay, so this is just to give idea. Of course, what time is 46 minutes. So, okay, so since we have a simulator, nothing prevents us to simulate also possible countermeasures. Okay, so in the injection attack, for the injection, the countermeasure against the injection attack is just to authenticate packets. If I authenticate a packet, I have to attach an authenticator to the message, which means that the message becomes longer, which means that that message requires more energy to be transmitted and requires more bandwidth. Okay? So by means of the simulator, you can evaluate the bandwidth and the energy consumption. Or, instead of authentication, you can simply increment the redundancy of the network. You just put more nodes. Okay, so which solution is the better? Is the best one? Okay, we can use the simulator once again to evaluate the best countermeasure. So I not want to spend more words about this. I'm going just straight to the conclusions of this part. So during the design phase, it's extremely important to determine the impact that possible attacks may have. We want to, because if I am able to determine this impact, I am able to rank the attacks and therefore to define security priorities and then choose which attack to manage, to select countermeasures and so on. Because as we said at the beginning, we cannot defend from all possible attacks. We have designed this framework, which is based on simulation, and which produces quantitative results, and which allows you to describe, let's say, analyze complex cyber-physical attacks. Of course, the work is not, let's say, this work is not conclusive. There are still other things that have to be done. First of all is to define some metrics for countermeasures, because as I described in the case of countermeasure for injection attack, you may have different countermeasures, and so you have another time you have the problem of choosing. Designing, basically, it's a matter of choosing. You have to choose one countermeasure or another one. so you want also to evaluate which countermeasures is better than the other. And also don't forget we have another dimension along with which we evaluate attacks, which is feasibility, because an attack can have a very high impact but very small feasibility. So I may neglect that attack just for feasibility reasons, whereas an attack with less impact could be more relevant just because it is very easy to be performed. Okay, so there are still steps that needs to be done before getting to the final solution. Okay, so this ends the first part. All the details can be found in these papers, and I repeat, I would be very glad if you send us some feedback. Okay. Still alive? Yes, it seems so.
I just have one
Please.
question. In your conclusion, you talk about metrics. In the slide, I think 32, you mentioned the list of how 32, I think. Just before that, yes, this one. So you're trying to evaluate the dangers of an attack. Wouldn't it be maybe misleading to say that the first attack is worse than the last one because of the choosing metrics? The choosing the right metrics wouldn't change dramatically this table?
Right. You said that this list depends on the metrics. So if I change the metrics,
you change the list.
Yes, you change the list. We, let's say, use metrics that are largely used in system theory, because basically those metrics measure, and please Ramiro if I'm wrong, so please correct me, measure how the system deviates from its correct behavior. No? Okay.
Wouldn't it be better to say that this list is for this kind of metrics? So
yeah, okay. This list derives from that metrics, but we are not going to change the metrics in a different system. Okay, so we would like to use those metrics.
But if we are talking about another system, it's another story. So
those metrics are used. They derive from system theory, and where they are basically the system is abstracted away. So they are abstracted away the actual application. Okay. Okay. So the second topic, let's say, that we look into within the Planet project is about a security architecture, and so the problem is more or less is the following. Most of the wireless sensor networks, even though while security is recognized as a problem, most of wireless sensor network applications don't consider security. Okay? And I guess this statement holds for IoTs too. Okay? The main reason is that at least so far, most of wireless sensor network applications are scientific applications. And in those kind of applications, security perhaps is not that important. But if you move towards the field of Internet of Things, then the kind of application, the services change, and therefore security becomes really important. At the same time, there exists a large body of software, of legacy software, that have been designed and implemented without security in mind. So the question is it possible to retrofit security into that body? Of course, without rewriting all the software. Okay? The correct way of doing would be the previous one, consider security since the designing phase. But since we have this lot of software, why don't we want to use it simply by retrofitting some security in this legacy software? So we have defined quite a simple architecture which allows us to do that. Basically, we have an application running, for instance, on a sensor node. We have a network stack, and in between, we put this component that we call star, which is the main topic of this part of the talk, which basically, whose task is to secure the communication in a transparent way with respect to the application. So the application must not notice the presence of star except for performance, because of course I put some computation. Okay? But the point is that this secures, let's say, the data that the application transmits in a transparent way. Of course, in order to do that, it uses cryptography. Then, therefore, it has to establish keys, to manage keys, and all these things is done by the other components of the system that I'm not going to talk about. I only let's say, recall that we have integrated several off-the-shelf key management schemes in these components. But now I am focusing on this. So this is basically the communication model. So the application sends a message. The message is intercepted by star. Star, let's say, secures the message, transmits it in the network. The message is received, it is intercepted by star, unsecured, and then handed over to the application. Okay? The application must not, let's say, notice the presence of star, and this means that star has to export the same interface as the network. Okay? Okay, so basically star implements a security policy. A security policy, let's say, allows you to define a flow, where a flow is simply a segment of traffic, and for each flow, the security policy specifies the transformations that you have to run in order to secure and unsecure the data belonging to that flow. And also, the security policy also specifies the keys that you have to use. For instance, this application can be, in this application, you may identify two flows. This could be, for instance, a data flow, and this could be a management flow, for instance, something related to the management of the application or something related to routing. And for instance, you want to protect them in a different way. For instance, the yellow flow, you want just to encrypt it in order to protect its secrecy, whereas the blue flow, you want to authenticate it in order to protect its integrity. Okay, so you have two different policies for two different flows. And of course, each flow needs to be labeled. I attach a label to every packet belonging to the flow, because on the receiving side, I need to know the policy to apply to that packet in order to unsecure it. The policy that I want to apply to a given flow, so a flow, just to fix ideas, could be, for instance, all the traffic addressed to a particular receiving node, or all the traffic related to a particular type of data. This is a very application-specific definition. The other thing we would like to have is that the policy that you apply to a flow can be changed dynamically. This is because the operating condition change, and initially maybe encryption could be sufficient, but after a while it cannot be sufficient anymore, and I want encryption plus authentication. And I want to change the policy without stopping the system, changing the policy and starting again. I would like to do that dynamically. This gives a very simple intuition of how this component is made. It is modular. It is composed of sub-components. We have this start-to application, which basically implements the same interface as the underlying communication system. I have this start-to communication, which adapts the start component to the actual communication system. And then I have the star engine, which actually applies the policy to messages. This is the component which actually encrypts and decrypts. Whenever I want to support a new communication stack, I have just to implement these two modules, but this module remains completely unchanged. Okay? If I want to add a new algorithm, so for instance, we support several algorithms, skipjack, SH1, and other algorithms. If I want to add another algorithm in order to extend the capability of this component, I have just to install a new module inside the star engine. Okay? Actually, we are able to implement algorithms at the software level and also at the hardware level. For instance, if you use sensor nodes which are equipped with CC2420, which has hardware encryption hardware capabilities, then we are able to exploit those capabilities by means of the star engine. This component is the only obligation that we leave to the application, because the starting point is to define flows, to define the segments that have to be protected. And the only one who is able to classify the traffic and to define segments is the application designer, is the application. Only the application knows if the packet is a data packet, a packet which conveys, I don't know, pressure value or a temperature value or whatever. Okay? So only the application knows the flows that it uses. This means that the application designer has to implement a function which receives a packet and which returns, let's say, the flow that packet belongs to. Okay? Each packet is labeled, and the label specifies the policy that I want to apply to the packet. For instance, policy could be encryption. I attack the encryption policy, the yellow label, so that on the receiving side, the receiver says, okay, this is the yellow label. Yellow means encryption. Okay, I decrypt the packet. If instead I use the blue label means authentication. Then when I receive the packet, I have to verify that the authenticator is good. Okay, so the label is something that is useful for the receiving side. And I have this component which attaches and removes labels to the packets. Finally, I have this sub-component which allows you to change the policies dynamically. Okay, so when it receives commands on this interface, I can change the policies that applies to a given flow in a dynamic way. This is an example of how star works. So when the application sends a packet, the packet is intercepted. So the application sees the same interface as here. So there is no difference for the application to be attached to start or to the communication stack, so I don't need to change the application. The packet is received, it is classified, and by means of the function I mentioned before, and then I detect the label that is the policy that I want to apply to the packet. I retrieve the policy, I apply the computations, and I send the packet in a secured way with the label which specifies the policy. The packet is received, and upon receiving the packet, the receiving star checks the label, detects the policies. According to the policy unsecures the packet, and then hands over the unsecured packet to the application. So the application does not noticing anything of this computation because everything is done in a transparent way. So from performance of this system, so we have for the moment we are supporting two communication stacks, the active messages and the CTP. And TinyOS, for instance, TinyOS, the application and star, the complete architecture, leaves more than 50% of the memory free, whereas TinyOS application, star, and CTP leaves around 36% of the memory free. So the memory footprint of our architecture is very, very, very reduced. So the memory overhead is very, very, very limited. Also, performance in terms of computation delay and energy consumption is very good. We are going to use this architecture in a practical problem, and in particular in the planet data collection experiment. So we are going to make this experiment in 2 weeks since now. The idea is that we have a wireless sensor network. The sensor network is clustered. Each cluster head becomes a waypoint for a UAV, and a UAV flies over the wireless sensor network and receives the data that each cluster has collected. Okay? In this kind of system, we can identify 3 different flows. A segment of traffic inside the cluster for cluster head management. You have to elect the cluster head, you have to rotate the cluster head. Okay, all this traffic is a flow. Then you have data collection within the cluster, so the nodes transmits their data to the cluster head. And the third flow is the traffic between the cluster head and the UAV. So we are going to implement 3 different policies for the 3 different flows using different keys and so on. Okay? We have also integrated CTP. I think you know this data dissemination protocol. Basically, it creates a tree between the sink and the nodes, and the data are collected through this tree. Let us suppose an application in which you have 2 data flows, one for temperature, another one for pressure, and and you also have another flow related to routing, because you have to build the data dissemination tree. Then you can use, for instance, star in order to protect these flows. And this is a coarse-grained application where there is no distinction between data flows, so the data are considered the same, and you just distinguish between data and routing. Data, you apply a policy to data and another policy to routing. But you can do something more fine-grained. Since star has very good performance, you could put a star at the higher level, and then you differentiate the policy between pressure and temperature. then these data are handed to a low-level star, which applies different policies to data and routing. So this policy is link level, this policy is end-to-end. So since star has this good performance in terms of computation and memory overhead, then you can afford to have 2 or more instantiation of the component. Okay, so oops, my energy is almost run out. Okay, the next steps that we would like to do is to, let's say, extend this project in order to use it in Internet of Things applications, not only wireless Internet of Things applications, in particular to extend STAR with access control policies, not only communication, secure communication policies. Okay, so 1 hour and 10. So there is the last thing I can introduce it, or just introduce very, very quickly, just to introduce the problem. So in many applications related to cooperating objects, very often you prefer to use time division multiple access as a protocol for medium access instead of an access medium access algorithm based on contention, which produces collisions. You prefer to use, in some cases, you prefer to use this. So the time is divided into superframes, and each superframe is divided into slots. And each slot is assigned to a node. So node 3 can only transmit in this slot, and so on and so forth. Okay? So this has several advantages, in particular in industrial wireless sensor network operating objects. Of course, you have guaranteed bandwidth. You have high energy efficiency because you have no contention. You don't need to spend any single joule in contending the medium access, the medium for communication. It is highly reliable because there is no collisions. And also it has low predictable latency. So there are several reasons why in this kind of application, and perhaps also in IoT system, you may prefer this solution instead of a content-based one. Of course, my adversary may always jump the channel. So it just puts noise in the channel and prevents me from communicating. It can always do that, and there is nothing you can do against this. It is a very strong attack. It is very effective because every node is prevented from communicating. But on the other hand, it is very simple to detect. And therefore, you could put in the system some measures, let's say, some emergency countermeasures aimed at safety. If I cannot communicate, I just stop. If I cannot communicate, I come back and land. Okay? So the system experiments in denial of service, but at least safety is guaranteed. But there is a more subtle variation of this attack, which is selective jumping. So my adversary doesn't want to jump completely this channel, but it wants to attack a particular node. For instance, he wants to attack node 3. So the adversary stays silent. So he eavesdrops, he observes, let's say, the slot allocation policy, and he notices that node 3 always transmits during this slot. So that since that moment, he jumps the channel only during this slot. In this way, it is able to prevent node 3 from communicating, but at the same time, it is not visible because it acts for a very small amount of time. Okay, and this kind of attack is very strong because the rest of the system continues to work, whereas node 3 stops working, and the adversary is almost not visible. Okay. So, which is a possible solution to this attack? Let's say attack which steals your slice. We have found a solution. Let's say an ad hoc solution and a general solution. I will give just a few intuition about the ad hoc solution. The ad hoc solution was for 15.4. As you may know, the 15.4 has, this is the super frame, this is time, which is divided into parts. An inactive portion where I can stop, can turn off the communication device, and the active portion. The active portion, a part is contention based, but the other part is without contention. So you have slots, and you make a request to the PAN coordinator of one or more slots, and the PAN coordinator allocates you those slots. Okay, so this part is TDMA, whereas this part is contention based. Okay, the problem with this protocol is that the message which transmits the allocation of slots to devices isn't clear. So the adversary is able to eavesdrop this message, realize the allocation, and then perform the selective jump. Okay? So the first step here I have a video where I have two nodes communicating with the PAN coordinator, and I have this node, the adversary, which jumps only this node. Okay? Okay, this is a screenshot of the sniffer, but I don't know, maybe you can't read it, but when the attacker is active, at some point you may see that node number 2 never this window report the value that are received by the PAN coordinator, and well, you cannot read, but from some point on, PAN coordinator only receives from node 2, from Bob. He is not able to receive from Alice because Alice is jumped. Okay, so Bob continues to transmit, whereas Alice is completely jumped. This is another way of seeing the thing. So in the normal case, both Alice and Bob are able to communicate, but under attack, Bob communicates, whereas Alice is completely jumped. Okay, possible solution. Solution is, the first step is, okay, since this packet is in the clear, I just encrypted it. What is more, 15.4 gives me a security sublayer which allows me to make this encryption in hardware, so I can do that very efficiently. Is this enough? Unfortunately, it is not, because it is true that the packet is encrypted and the adversary is not able to read it, but the adversary can still analyze the traffic. So the adversary sees when Alice transmits. So Alice transmits in the 4th slot, and then from that moment on, the adversary jumps the 4th slot. Okay? So this is part of the solution, but this is not the solution. So which reminds me that this is a very famous quote from Roger Needham and Butler Lampson. Whenever anyone says the problem is easily solved by cryptography, it shows that he doesn't understand it. Okay? The other part of the solution consists in shuffling. So I cannot keep the allocation constant, but I have to change the allocation for each superframe. I have just to shuffle, okay, when I play cards. Okay, I just change the allocation in a random way, in a way that is not predictable for the adversary. Okay? And okay, I have now I have the same attack with both countermeasures in place, and well, the result is that now both Alice and Bob can communicate, because the adversary does not know when, in which slot, Alice is going to transmit. And the only thing that he can do is just to shoot at random. Okay?
Sorry.
Pardon. Okay?
Who is choosing this random allocation? The coordinator?
The coordinator.
They tell the other nodes, they tell the other sensor to change the slot.
The coordinator changes the allocation of the slots to nodes. So if you are a node, now you get slot number 1. In the next super frame, I'm the coordinator, I shuffle the slot and I give you the slot number 3. This allocation is unpredictable. Since it is random, it is unpredictable for the adversary.
It can be intercepted by the attacker.
It can be intercepted, but the allocation is encrypted, so it is not able to read it. The only thing it can do is to shoot at random, in the hope to catch it. Okay?
Normally, you are not shuffling the slot allocation type how often it's transmitted by
At every super frame. So
you don't reach it and it goes much overhead by doing this?
no. The overhead is minimal because shuffling there are very efficient algorithms. I think they are logarithmic in the number of slots. So the shuffling algorithm is very efficient. Encryption is very efficient because it is a random. It is in hardware. It is performed by the communication device, and you have to transmit the new allocation every super frame. So this are just some bytes, some tens bytes, which are, let's say, distributed all over the whole super frame. So in a percentage way, they have, their weight is negligible. Okay. So the other view. So this is the situation in the absence without the attack. When the attack, with the countermeasures, when we have the attack, both Alice and both Bob are able to communicate. Of course, I have a little loss of performance because the adversary shoots at random, and from time to time he is able to catch the right packet. Okay, so from time to time, either both Alice and Bob are hit by the adversary. The loss is 13.8% because the number of slots that 15.4 manages is 7, and therefore there is one probability out of 7 to be hit, which is exactly this number. Okay, I'm going to finish. We have solved this problem also in a general, completely distributed system. So where there is no coordinator, and where all the nodes have to. So the problem is that the shuffling is not done by the coordinator, but it is done by every node in a distributed way. So there are some tricks to obtain this. I'm not going to tell about it. Okay, so the details, you can find all the details in the paper. I'm going to present these things next week at this conference, the Emerging Technology and Factory Automation Conference. Okay, conclusions. So these are the results of part of our activity in Planet. In the project, we looked into security since the first day. It was one of the main requirements of the project. We moved from real concrete experiences. We made realistic assumptions. We consider real plants, real systems, and also we tried to have as broad as possible view of security. Not only find a solution to a specific problem, but also to give a contribution in the architecture and also in the design phase. Okay, and this concludes my talk.
Thank you very much. So, are there any questions? Maybe just one question. We often see also in every, not in every, but in many security algorithms, we have seen also this shuffling is based on random. But I know that random is never random, but pseudo-random.
Right.
Sometimes there is this probability.
Yes.
Have you done, or do you have some feeling if the adversary tries to, let's say, listen for a long enough period of time and gather some statistical information to try to probabilities and not try to put also some other pseudo-random. So how far he can increase, the adversary can increase the effectiveness of the attack, except for this 13.8%.
Okay, so in the centralized version, you can have, you can have a truly random generator, because you have only one. So you have the pan coordinator which shuffles, and if you have enough money, you can attach to your pan coordinator a truly random generator. Okay, so in the centralized case, coordinator can be the generator can be truly random. So you can have a physical hardware random generator.
So the point is that the adversary is not synchronized with it. That's the point.
Right.
Because theoretically, adversary could have also.
I am talking about. Perhaps I didn't stress this thing properly. I'm talking about secure random generators. Okay, so a generator that in an adversary, so it is seed by means of a secret, and that an adversary cannot interfere with. And it is a kind of generator such that even though I have observed a sequence of bits, I am not able to forecast the next one. So I cannot use any simulator I cannot use any generator that is used in network simulation, for instance. Secure generators are particular subset of generators. In the centralized case, I can use a truly random generator, truly random secure generator. In the distributed way, in the distributed case, since each node has to shuffle, so I have to do this shuffle in a distributed way. So each node makes the shuffling, but all the shuffling must be consistent with one another. In other words, all the nodes shuffle the slots in the same way. In that case, the simulator, the generator must be still secure, but must be pseudo-random.
Because so kind of synchronized.
Right. Anyway, the node has
in a way that adversary cannot synchronize.
Right.
Because
right.
Otherwise, he will also shuffle.
Of course, the shuffling depends on the secret that the nodes share. Okay, and of course, the node must have some form of synchronization, because we are talking about the TDMA system, and therefore some form of synchronization must exist. But the nodes share this secret, which allows them to shuffle in a secret way, in a way that the adversary is not able to predict. Okay, and of course, the generator must be a good one, and we used a cipher, which is for our purposes good enough.
Thank you.
Please.
About the case one, you said there's a contention window. What kind of contention it is? I mean,
Is the usual CDMA, collision detection multiple access.
okay.
But we are not interested in that part.
No, because my
This is the normal. This is the normal medium access protocol for 15.4 with collisions and all
okay,
that
so
kind of stuff.
collision detection.
But we are not interested in that part. We are interested in this one. So if you, for instance, have some quality of service requirements, then you want to be, you want to have guarantees about when and for how long you are able to communicate. For this reason, you can exploit this part, which is especially dedicated for this. You ask one or more slots, and you are guaranteed that you are the only one who transmits in that slot. So you know exactly when you are going to transmit and for how long.
Okay, because my concern was about how many data have each node to transmit, because otherwise, if you are spending time on contention, I mean, if you are spending time on contention, I would expect each node to spend a lot of time. I mean, really needing that reservation because the data are like good amounts. So.
Yeah, well, I mean,
But
this
was not a part of the.
No, this is a general problem. If you have a large amount of data to transmit, of course you let's say you occupy the medium for long, and the probability of and the chances for the other one to get the medium decreases. Of course, if you go for a TDMA approach and you have a slot, you have to transmit all the data that fit a slot. You cannot transmit more. And these are for applications, for instance, for real-time applications or quasi-real-time applications. So they are not for instance, for streaming videos. But this is for industrial applications or for control applications. Yes.
Just we have this out of scope, but how do you actually request for these slots? So it's not in the convention phase, it's something.
Okay, it is part of the 15.4 protocol. I didn't enter into these details. So a device can make a GTS allocation request at any time in the super frame. So, and the path coordinator at the beginning of the next super frame transmits a beacon with the GTS fields allocated. So, and similarly, at some point you can also send a GTS deallocation request saying that I am not interested in that slot anymore. Please use it for someone else. Okay. So this is a detail related to the protocol, and I completely.
I don't know if you have heard, but it's mostly like reservation aloha.
Yeah, I think that 15.4 hasn't invented anything new.
Yeah.
So the novelty is not in the protocol, but the novelty is in at least is in the way is in the attack, because the attack is quite new. The attack hadn't any solution before, and the novelty is in the solution that we have found, which is effective and also good performance.
Okay, so thank you very much.
Thank you.